The purpose of this demonstration is to provide you with an introduction to the value modeling component that can be used for performance management and proactive replanning. The assumption here is that the objectives and the overall scope of the model have been introduced. What we're going to do here is give you a sense of what such a model looks like and the type of functionality it offers within the context of an opencast mine. First, let's look here at how we're presenting the model in terms of the physical structure. The mining operation is positioned as the main node of this tree. Under the mining operation, we have the material movement or mining process, as well as processing, servicing, and financials. Expanding the material movement node displays the specific activities comprising material movement, in this case, drilling, blasting, loading, and hauling. If we expand each of these activities, we can see the activity comprises specific fleets, and under each fleet, we have specific equipment. We also have the costs that are prevalent for that activity, which are modeled at activity level, fleet level, and equipment level based on the data availability. Blasting is modeled purely from the perspective of costs. The assumption is that we can blast what we're drilling, and it's just a question of how many resources are being used in blasting. The loading activity is broken into fleets, and under each fleet we've got the major piece of equipment comprising that fleet. With hauling, we've stopped at hauling fleets. The design allows for expansion to equipment or equipment vintage categories in future. Now, we'll look at the processing side of the business where we see the crushing, milling, bulk flotation, bulk tails, copper moly separation, leaching, and shipping nodes. Some of these nodes are broken into more detail. For example, crushing has the specific crushers modeled, and milling has each of the specific lines of each mill modeled. Bulk flotation has the bulk lines modeled here, and under each bulk line is a recovery and cyclone overflow model. The recovery model models the behavior of each kinetic class. The cyclone overflow models the size fractions per float line accordingly. Each line has its own recovery and kinetic class submodels. The services component of the model will represent the costs associated with the non-production activities. The financials component will model the conversion of the copper produced and recovered, etc., into revenues leading up to operating profit. Using hauling as an example, we'll show you how each of these objects that make up the structure of the model is modeled in more detail. If we click on the 793 fleet, we can see a series of variables or attributes that describe the 793 fleet. Some of these attributes are straight inputs. Others have equations that model the behavior of the 793 fleet. If we expand any of these attributes, we can see that they're time-based, whereby we're modeling something that has happened historically, and if we scroll forward, we can also model what can happen in the future under different scenarios. What's useful is to be able to see these attributes in the form of the relationships governing them. If we switch to the canvas view, we can see these attributes organized based on how they're actually being modeled in terms of the underlying equations. We see that at the top, we have the tons hauled, which are in turn driven by the tons hauled per vehicle, times the number of vehicles, or the number of equipment. That in turn will give us the total tons hauled for the hauling activity for this particular month, January 2011. In turn, the tons hauled per vehicle are a function of the tons per hour times the net operating hours, and the net operating hours are broken down into gross operating hours, unutilized hours, available hours, standby hours, and so on. The data is sourced from the Wencode dispatch system, and this is what gives us the opportunity to get to this level of detail. On the tons per hour side, we're modeling it in terms of average payload, which is a function of the fill factor and the truck capacity, and also the number of cycles per hour, which in turn is a function of the cycle time. The cycle time is a function of the different operating times, waiting at the dump, waiting at the loading unit, etc. The empty travel time and the hauling travel time here are just recorded as times, but they will be modeled in terms of distance and speeds. With a model structure like this that's been populated with numbers for January 2011, where we're modeling the actual tons hauled for that month based on the specific underlying drivers, we can now perform out-of-the-box analyses, such as a sensitivity analysis. We can now ask Carbon to look at tons hauled and flex every attribute or driver at the leaf level of the tree structure by 10%. The software will in turn tell us what the impact is on the tons hauled. The y-axis displays the drivers, and the x-axis displays the impact that they have on the tons hauled. If we ignore things that we can't influence or where we're at the maximum, such as scheduled hours, we can see going down the tree that the truck fill factor is one of the most important drivers of tons hauled. A 10% change in fill factor will have approximately a 900,000 ton impact per month. Obviously, if we increase truck capacity and number of equipment, it has a similar effect, but those require capital expenditure, whereas the truck fill factor doesn't. Truck fill factor is something we need to manage very carefully on a day-to-day basis, because it is the single biggest driver of value that we can control in the short term. The next most important drivers are the hauling travel time and the empty travel time. As mentioned earlier, we will, within this phase of the project, break those down into distance and speed. We also have a series of other time-related factors that influence our tons hauled, such as lunch, shift changes, standby, etc. We may have less control over some of these, such as lunches, but perhaps shift changes poses an opportunity to improve. As we can see here, a 10% in shift change time improvement will give us an almost 100,000 ton benefit per month on this specific fleet. We also have out-of-the-box analyses that allow us to visualize these variables in a different way in order to better understand them. If we click on the net operating hours, for example, and we select a waterfall chart, we get what is essentially a type of Pareto analysis that we can perform. What we see here, based on the tree structure, is that our net operating hours are equal to our gross operating hours, less our unutilized hours. We can drill down into those unutilized hours by simply clicking on them. This shows us that our unutilized hours are composed of non-operational delays and operational delays. If we click in the operational delays, we can begin to understand these a bit better. Weather is a big component which we may not have control over, but thereafter it's the shovel availability that's a problem. This gives us a different perspective of the underlying value driver tree structure, which allows us to understand where the things are that we need to focus on. I also have the option of going to another configured screen that allows me to view the whole tree structure in terms of a comparison between actual and target. Over here, I can see that my actual was 8.8 million tons for this month, but my target was 9.3 million. Of course, I'd like to understand why that is. The obvious approach is to go down the tree and manually understand where these variances were, so I can understand what drivers drove the difference. An easier way is to right-click and select an attribution analysis. By virtue of the relationships, the model will compute which variables were responsible for these variations and by how much. I can now see that my truck fill factor was my biggest contributor to my variance between my budget and my actual. In real numbers, a 4 percentage point difference led to an almost 400,000 ton loss. My shift change time and my engine time relative to my target were also big contributors to my reduced tonnages. Although there were a number of other drivers that resulted in higher tonnages, my net effect is a loss, predominantly because of fill factor. I can also get a time-based comparison graph between my budget and actual hours for any of my variables by simply clicking on each variable. In the final model, we will have an auto-forecasting mechanism that will forecast each of these drivers based on some rule related to historical performance. The insights gained from the model enable us to perform a what-if analysis that allows us to do short-term replanning in order to improve the value for the business. This capability is derived through a series of easily created and configured dashboards. This is an example of one such dashboard from a generic OpenCast model. The dashboard displays each activity on the mining side, the drilling, loading, and hauling, as well as the primary drivers of value for each of these activities. This type of dashboard allows you to take into account the systematic effects of making changes to a specific activity. For each activity, the drivers of value were selected based on the sensitivity analysis that we saw earlier. On the top left, we have a graph of the tonnages that are being produced for a particular period. The dark blue bar represents the tonnage as is, and the light blue bar represents the tonnage under a scenario that we're going to run by changing the levers. On the right here, we have some financial output, such as profit and revenue. For example, we can increase our truck fill factor by a certain amount based on analysis we've done and by eliminating variability in our fill factors. We could also have conducted analysis indicating that we can increase our speeds by 10 to 15% by eliminating variability and having more consistent truck speeds. Just by focusing on these drivers alone, we can increase haulage from 79 million to 90 million tons annually. Note that there's no impact on the profitability at this stage, as we still need to make a conscious choice as to how loading and drilling will deliver on the additional capacity. First, we'll increase the average truck load on loading, which on its own will actually reduce tonnages per annum. The reason for this is that the shovels incur another pass, because we haven't increased our fill factor on our shovels. By increasing the fill factor to approximately 91%, we can harness the benefit of the additional truckloads. To increase our loading capacity to that of hauling, we can use the waiting for truck per cycle lever here to reduce the time that the shovels wait for the trucks. Profits haven't increased, as we still need to amend the drilling levers. As we decrease the standby time, not only do we increase the tonnages to the same levels of loading and hauling, but also we produce over $100 million in incremental profit. As you can see, this simple dashboard easily allows you to adjust the levers to the extent that you think is viable in order to see what the financial impact is, whilst paying respect to the system effects of these changes. This allows management to do quick short-term replanning in order to prioritize what is best to focus on to drive value.